Everyone has seen them, and have probably teased many cats with them. Maybe some of you have had unwanted hair removed. Or maybe you have built one and popped some balloons with it. Bottom line, lasers are ubiquitous not only in scientific research but also in industry. Just how do these little devices manage to put out that nice powerful collimated beam of light? All this and more coming up. As some may or may not know, laser is actually an acronym. It stands for light amplification by stimulated emission of radiation. However, nowadays it is so common that people don't bother to capitalize it and simply write laser. A very brief history of the laser starts in 1917 when Einstein introduced the concept of stimulated emission, which will be explained shortly. Then in 1954 the first maser was demonstrated by Charles Townes. The M standing for microwave. The ammonia maser was the first device based on Einstein's predictions and obtained the first amplification and generation of electromagnetic waves with a wavelength of about 1 centimeter, which is in the microwave range. This is recognized as the precursor to the laser. It wasn't until 1960 when Theodore Meyerman developed the first working laser at Hughes Research Lab. Meyerman's early laser used a powerful energy source to excite atoms in a synthetic ruby to higher energy levels. The development of the laser was a collaborative effort by scientists and engineers who were leaders in optics and photonics. Okay, so why are lasers useful? Why are they ubiquitous? The answer can be broken down to 3 unique properties the laser holds. The first being line width. The purity of a laser, referred to as the line width, can be quite narrow, more so than any other light source. In layman's terms, this is a measure of what frequencies are contained in the emitted light. The narrower the line width, the closer the emitted light is to a single frequency, single color if you will. Thus, a laser is said to be monochromatic. In reality it does output a small range of frequencies. The smaller this range, the better the line width and quality of the laser. In contrast, an incandescent bulb has a very large line width and emits a broad spectrum, which is why the emitted light is white. White light is a superposition of all the colors in the visible spectrum. Having a narrow line width is useful because many scientific experiments want to analyze stuff with certain energies. Different wavelengths of light correspond to different energies, hence having a source with one energy is helpful. The second is coherence. The light emitted by a laser is coherent light. This means it is all polarized in the same direction as well as being in phase. The laser is said to output highly coherent monochromatic light. An LED on the other hand is also monochromatic, one color, but it emits incoherent light. An analogy with synchronization and harmony can be made. Imagine an orchestra playing. If the orchestra is in sync and everyone is playing the parts correctly, it will be pleasing to the ear, the laser. If some players are playing out of sync but still playing the parts correctly, it won't sound as good, the LED. Coherence is important because all the photons add their energies together, and we can then focus them on a small spot over some distance. Lastly, power. Lasers make it possible to deliver high-intense light to a small area. Of course, militaries are particularly interested in this aspect of the laser, as well as medical applications. Laser eye surgery, for example. Now let's take a look at how a laser works. The workings of a laser are quite complex, as it requires an understanding of quantum mechanics. There are some commonalities behind every laser. The first part can be broken down to 3 key pieces: stimulated absorption, spontaneous emission, and stimulated emission, which is what the SE part of laser stands for. Let's take a look at the first concept, stimulated absorption. We will need a nucleus that is made up of protons and neutrons that has an overall positive charge, and an electron that has a negative charge. Hey there, little guy. Most textbooks show electrons existing in discrete energy states of a material. But actually, electrons exist in probability density clouds around the nucleus, as they have wave-like behavior, and the orbitals represent the average distance one is likely to find it. Let's use this average distance to define the orbital, and ignore the probability distribution for simplicity. Mostly always, electrons are found in the lowest energy state, or ground state. Everything in nature wants to be in a low energy state, as it is easier for it to exist at this level. In other words, it minimizes energy. Think of a ball on a hill and how easy it is for it to roll down. It wants to roll down because the energy state is lower closer to the Earth's core than further away, in this case potential energy. However, it is possible to excite electrons by some kind of external means. Just like we can exert a force on the ball that has rolled down and push it back up. Light can be this push to excite electrons. If a photon of light, which is 1 unit of light, comes across an electron in a low energy state, it can sacrifice itself, and push the electron to a higher energy state. The photon is annihilated, but the energy of it is now part of the excited electron. It should be noted that each material has different levels of energy. In other words, if the ground state is 1 unit and the next energy level is 5 units, then the photon of light must have exactly 4 units of energy to excite the electron to that energy level. Anything lower will not suffice and anything higher would not as well, as there is nowhere for that extra energy to go, unless a higher energy state exists. If the incident photon is very high in energy, the electron would be ionized. To continue our analogy, it would be like trying to push the ball up the hill with not enough force, the ball would just roll back down. Too much force and it would roll down the other side, go to another plateau, or be launched into space. An exact amount of energy is required to elevate it to a particular energy state. Again, this process is called stimulated absorption. As we are stimulating the electron and it absorbs the photon's energy. The next mechanism we will look at is spontaneous emission. We now have an excited electron. What happens now? Well, again, this higher energy level is quite unstable and after a very short time, about 100 nanoseconds of being there, the electron will eventually fall. For some perspective, light travels about 29 meters in 100 nanoseconds. When it falls back down it will release a photon with energy equal to the difference in energy levels. The higher the fall, the higher the energy of the photon will be. Should the energy value of the photon that is released be in the visible range, we would perceive it as color. You may be thinking, if the electron reaches the higher energy level through the previously mentioned stimulated absorption mechanism, why exactly does it fall back down? Well, referring back to the ball example, imagine the ball on a hill, but now with the top having zero friction, and a sharp point. The ball can remain there only if it is perfectly balanced, but any tiny little force in either direction will cause it to start rolling. The electron in this higher energy state is in a similar situation. The forces that push it are small perturbations in vacuum energy. This is a quantum mechanical effect. Space or vacuum is not as empty as we think. Things are popping into and out of existence constantly. It is these vacuum events that perturb the electron. This is also responsible for why things are ferromagnetic. That's a different story though. Again, this process is called spontaneous emission. As the process that the electron falls back down to the lower energy state is more or less spontaneous. The last quantum process we will talk about, and the most important for lasers, is stimulated emission. This occurs when a photon interacts with an electron that is already excited. This photon can act as a type of perturbation, and force the electron to fall back down to a lower energy state and emit a photon. We then will have two photons. Photons actually like to be together. So if one comes near a situation where another one could be present, such as the electron falling back to a lower energy state, the situation usually will play out. The important part is that the emitted photon will be identical to the one that stimulated it. Meaning same frequency, phase, and polarization. They will be coherent with each other. So, if we could somehow avalanche this process, we would have a laser. After all, that is basically what a laser is. A zillion identical coherent photons being emitted. In contrast, if two electrons undergo spontaneous emission, the emitted photons will unlikely be traveling in the same direction, nor be in phase. But in order for electrons in the excited energy level to be able to undergo stimulated emission, and not spontaneous emission, enough time has to be available. The lifetime of an electron in the excited level is just too short. However, some materials have so-called metastable states. These are excited states with slightly lower energy than the excited states. These states allow the electron to remain there for much longer lifetimes, milliseconds instead of nanoseconds. enough time that a passing photon can cause it to undergo stimulated emission. Of course, an initial spontaneous emission from the metastable state to the ground state must occur in order to have the initial photon that can stimulate other excited electrons in the metastable states. To sum up, if a ground state electron is hit with a photon, it will absorb it, and move from the ground state to the excited state. The photon must have the energy equal to the difference between these levels. This electron will then transition to the metastable state, if one exists. This transition does not emit a photon, and is said to be a radiation-less transition. The energy difference is dissipated in other ways, heat or phonons. Now this electron, if a photon stimulates it, will emit a photon with equal energy, phase, and direction. These are the ones that make up the laser beam. It should be apparent that the photon which pumps the electron from the ground state to the excited state has a different energy than the photons that are being lased. This is because the energy difference between the ground state and the excited state is different than the difference between the metastable state and the ground state. The pumping photons are always higher in energy than the photons being lased. We obviously want lots of electrons in this metastable state, more so than the ground state, in order for them to be in a situation where stimulated emission can occur. Something known as creating a population inversion is required. If we only had two levels, we would reach a point of saturation, where 50% of the electrons are excited, and 50% are not. The excited electrons simply spontaneously emit too fast, essentially our medium becomes transparent to photons. By introducing the metastable state, we force the pumping photons to excite the ground state electrons, that then transition to the metastable state, so the photons that are emitted by the transition from the metastable state to the ground state are primarily used to stimulate other electrons in the metastable state. Enough time exists for this to happen. Yes, some of these photons will excite ground state electrons directly into the metastable state, but the pumping photons should take care of the majority, and create a situation where there are more excited electrons in the metastable state than ground state electrons, a population inversion. By the way, the above is describing a 3-level laser. 4-level lasers exist and are more efficient. Again, we want to create an avalanche effect, where the spontaneously emitted photon that was created when an electron transitioned from the metastable state to the ground state, gets amplified through the means of stimulated emission. We don't want just a single puny photon, we want lots, all working together. It is not practical to create a laser that is extremely long, so the solution is to put the laser medium in a cavity. Let's take a closer look at how a cavity will influence the light waves, and how exactly this will create the amplification we desire. Since light is a wave, it will be subject to constructive and destructive interference. We want constructive interference in our cavity to take place, in order to have a high-intensity beam. A laser cavity has a mirror on one side and a partial mirror on the other. It is partial because we want some of the beam to escape, that's the beam we see. Now when light waves are created through spontaneous emission, they will initially travel in random directions. But the ones traveling perpendicular to the mirrors will reflect back and forth. Let's take a look at one of these light waves. It is first emitted via spontaneous emission and quickly becomes large in amplitude through stimulated emission. It travels towards the mirror, and is reflected back. Because we continue to stimulate atoms in the left and right directions, we get two waves in the cavity. Again, one moving to the left, and one moving to the right. Waves will add their amplitudes when interfering with each other. In this case, we will get a standing wave. Meaning instead of a wave noticeably moving to the left or right, the combined wave will appear to be going up and down. Rest assured, this is just an illusion. This is the effect of two waves hitting each other head-on, and their left and right components cancel out, but their up and down components add together. So when the wave looks flat, this is a moment when the two waves are destructively interfering with each other, and at the maximum they are in a constructive interference point. Here are a few examples of some standing waves in a cavity that are resonating. Resonance is just a fancy word for having these waves being in a state where standing waves are being produced. A mode being just what n you have, n equals 1 is a mode, n equals 2 is another one, n equals 3, etc. Is there an equation that will tell us what modes can exist in the cavity? Sure there is. The left part is the frequency that exists in the cavity, n is the mode, which is always an integer, v is the velocity of the wave, and L is the distance between the two sides of the cavity. The velocity in our equation is the speed of light, c, which is 300,000 kilometers per second. The L is just the distance between the mirrors. Light traveling from the left of the cavity will now interfere with light traveling from the right. So again, we have these possible modes where the light can produce standing waves, and be in resonance. Not all frequencies are able to exist in a cavity, but a lot are. Also, let's be clear that the standing waves produces are a collection of trillions and trillions of light waves all working together. They are produced by stimulated emission, and the cavity allows them to keep amplifying each other. They are coherent with each other. Recall, this was one of the big reasons why we care about lasers. If we didn't have this synergy between light waves, we would just have an ugly LED. I bet you can't make your cat go crazy with a red LED. Well, maybe, but you get my point. Question: what frequencies are allowed to exist in a red laser pointer's cavity? Answer: a cheap red laser pointer has a cavity length of about 1 mm, and the speed of light is c, 300 million meters per second. Plugging in these values to our equation, we would get a difference between allowed frequencies of about 150 GHz. Now, red light has a frequency of about 400.05 THz, which corresponds to an n value of 2667. Recall n must be an integer. So if 400.05 THz is an allowed frequency, then the next one would be when n equals 2668, which is a frequency of 400.2 THz. We can plot all allowed frequencies, as we know 150 GHz will separate them. The plot will look like this. Here we have n equal to 2667, and the corresponding frequency of 400.05 THz. Here is 2668, 2669, and so on. These are the frequencies that are allowed to resonate in this laser cavity. So if you wanted your laser to have a frequency of 400.1 THz, you would first have to change the cavity length for this to be allowed, as it is not possible in this red laser's cavity. About 2600 frequencies in the visible spectrum would be able to resonate in this red laser's cavity. Now, there is slightly more to the story about these allowed frequency lines. We have assumed the mirrors are perfect, which is practically impossible. The imperfectness of the mirrors and other slight variations add a thickness to the frequency lines. The actual allowed frequencies in a laser cavity looks like this. Again, this is due to imperfections. The last piece of the puzzle is to mention the gain medium itself. Gain medium is just the material we are using for our laser. Different materials will have different energy levels, hence photons of different energy will be released during stimulated emission. For example, different materials will need to be used to create a blue laser than that of a red laser. Since the energy levels in a material are discrete, one would think that exactly one frequency would be emitted out of a laser, but only if this is also a frequency allowed in our laser cavity. We can superimpose these ideas on this graph. We assume here that indeed the stimulated emitted photon is a frequency that is allowed in the cavity. However, there is much more to the story. The frequencies being emitted out of the laser actually takes a shape like this. This was briefly mentioned at the beginning of this video when discussing line width. What is going on here are complicated events such as the Doppler effect, Stark effect, and other quantum mechanical behavior. The takeaway is that the gain medium does output a small range of frequencies, and has this gain curve. It is still extremely narrow, and said to be monochromatic. It's not, but it's close enough. To sum up, certain frequencies are allowed to exist in a laser cavity. There is some relaxation to these frequencies as the mirrors and such are not perfect. The laser gain medium emits photons in a certain frequency as well, but again there is some broadness to this as certain effects influence this. We can superimpose these two frequency plots and get the following. The frequencies under the gain curve that have enough intensity to overcome other cavity losses are the ones the laser emits. There are plenty of laser active medium these days. Any frequency you wish to lace is pretty much possible. Here is a picture of different laser material, and the frequency they output. Some are in the gas state, some solid, and it is even possible to use a liquid as a lacing material. This concludes this episode on the laser. If you enjoyed the content and learned something, please consider doing all that stuff every other video asks you to do. You know what I am talking about.